Good afternoon. Welcome to the elementary principles of chemical processes. Um, okay, settle down, please. Okay, right. So today, we are going to talk about non-ideal gases. Um, before that, I hope you know some of the idea about the ideal gases. You know, ideal gases normally is we think that it should be applied in the condition of the high temperature and low pressure. The high temperature means that the temperature normally need to go up more than 0 Celsius. The low pressure means that the pressure need to go below 1 atm. And under this condition, we will regard the gas in this environment will be ideal gases. Okay, if this if the ideal gases apply in a case, so the ideal gas equation of state will apply. We can use the equation of state. Ideal gas equation of state will be PV equal to nRT, and sometimes we use PM equal to DRT. Right? D stands for density. Right? M stands for molecular weight. Right? And sometimes, so this is important for you to know that ideal gas. What is ideal gases? Okay, so ideal gases is important for you to start to understand the relationship between the pressure and the temperature. Okay, and today we are going to talk about the equations of the state for non-ideal gases. So let's recall some of the things we know. This is the assumptions of the ideal gases equation. You know, ideal gases equation can be derived from the kinetic theory of the gases by assuming some of the conditions. First is that the gas molecules has a negligible volume. So we don't think that the gas has a volume. But as a matter of fact, you know, the molecule occupy some spaces in the room, right, in a container. So, but ideal gas, we think that there's no volume for the ideal gas. And second is that exert no forces on one another. So there is no interaction between molecules in the chamber or in the container. So there's no force interaction. But again, they do have interaction, right? And the third assumption is that they collide elastically with the walls of their containers. That means what? That means when the molecule hit the wall, there's no energy exchange. Again, they do have energy exchange, right? Because if you have high pressure, you will have energy exchange, right? But anyway, this is the assumption of the ideal gas, and then we can apply this for the ideal gas equation. So if you want to compare the real gas and the ideal gas behavior, you can realize that in the world, there's no ideal gas that exists. As I just want to tell you that there's no absolute zero vacuum, okay, in the world, and there's no 0 Kelvin in the world. So this is ideal. 0 Kelvin is ideal. It's very difficult to achieve, and 0 atm is ideal. It's difficult. It's impossible to achieve. So that means that the ideal gas is not exist. Because what? Because the velocities of the molecules are very high. So the speed of the oxygen or nitrogen will be a few hundred meters per second. That means the molecules of the nitrogen or oxygen move very, very fast. Once it moves very, very fast, you know, this speed of the airplane, right? Speed of airplane, speed of the sound, right? Okay. So the collides are so numerous. So the molecules hit each other very often. So a few times 10 to 23 third per square centimeter. So it can collide very often. So the impact time is very short and the transfer of the momentum very abrupt. So as you can see these two figures, if we regard PV divided by RT, if it is 1 mole, and this dashed line represents ideal gas. But when you check with the increase of the pressure, none of the gas lie on this line, this dashed line. For example, like nitrogen, if we increase the pressure, it will drop first and then go up to more than 1 and then increase rapidly once the pressure increase 200 atm, 400 atm. This is very, very heavy pressure, very, very high pressure, right? Okay, not only depends on the species, but also depends on the temperature. As you can see, if we have the same molecule and then we increase the pressure together with the temperature, as you can see that the low temperature has a higher differences. It's 20 Kelvin, which is below 0 Celsius, right? So you can see that it doesn't behave like ideally. The gas doesn't behave ideally, right? Okay, so as you know that with the temperature and pressure change, the ideal gas behavior is not exist. So today, what we want to talk is that we want to let you realize there are some equations which is used for the non-ideal gases. But before we talk about this, we need to know two terms first. One is called critical temperature. One is critical pressure. So what is critical temperature and what is critical pressure? Let's so the ideal gas, we normally regard this condition will be in high temperature, which is more than 0 Celsius, as I just told you, and low pressure, which is less than 1 atm. And then how well or poor the gas equation of state fit PVT's data for a species often depends on the values of the system, temperature and pressure, related to the two physical properties of the species. So the temperature and pressure were related to two physical properties of the species. So what are these two? What are these two? One is called critical temperature. One is critical pressure. Okay, so who are they? What are they? So every species of the gases has their own critical temperature and a critical pressure for a single species. For example, oxygen has his own critical temperature and pressure. Nitrogen has his own critical temperature and pressure. Water has his own critical temperature and critical pressure. So you can check this out. You can look it up at table B1 in your book. Okay. So this is one of example is that, for example, carbon dioxide, the critical temperature is 31.1 Celsius and the critical pressure is 73.8 bar. I will give you a bit roughly ideas. 1 atm is equal to 1.01325 bar. So 73.8 bar means it's around 73 is around 73, right? atm, something like this. Okay, so this is the case of the carbon dioxide. How about water? Water here is that the critical temperature is 374.2 Celsius, and the pressure is about 220.5 atm or 220 atm. Okay, you don't need to remember this number, but you need to know what is critical temperature, what is critical pressure. I'm going to show you what are they. So here is the experiment. This experiment related to the T sub C, right? C stands for critical. So this is critical temperature. P sub C is C stands for critical. So this is critical pressure. And these two will be related to supercritical fluids. So what is supercritical fluids? Okay, let me give you an example of the using the case of water. So this is the vapor. H2O is in the gas phase. There's no water. There's no liquid water here. Okay? So, for example, in this condition, there's no liquid water, only gas, H2O. And then the temperature here is T1, and pressure is P. Okay? And then if we keep the temperature as a constant, and this is a piston, and we push this piston down, that means what? That means the pressure will increase, right? That means the pressure will increase. Okay, so we push this piston down, and we keep this environment as a temperature T1 only. There's no change of the temperature. Obviously, pressure increased. And then, so if you keep on pushing this piston down, and you will realize one day, or there's a moment, the first drop of the water will appear. You will see the first drop of the water, which is in liquid, right? So these are all the vapors of the H2O. And then if you increase the pressure, first drop of the water will come out. Okay? And at this moment, we measure the temperature and pressure again. Right. So let's say the case of the T1 equal to 100 Celsius. 100 Celsius is the boiling point, right, of the water. So you can assume at this moment there is no liquid exists. Okay, and at this moment the pressure will be what? The pressure will be 1. Okay, and you started to push a little bit. Pressure will be a little bit higher than 1, right? Okay, so at this moment you can see that this time the vapor pressure will be 0.5977, which is very low. Sorry, the density of the vapor. Okay, at the density of liquid will be reached to about 1 gram per cubic meter, which is 1,000 kilograms per cubic meter, right? Okay, this is common sense, right? Because you know the density is about 1 for the water, right? Okay, and at this moment, there are 2 phases. One is gas phase, one is liquid phase. Okay, so this is easy to understand, right? Let me say this again. At a temperature 100 Celsius, and the pressure is 1 atm, you know this is the boiling point of the water. And then we push this piston a little bit down, a little bit lower, and then the first drop of water will come out. And we realize the density of vapor is about 0.5 or 0.6 kilograms per cubic meter. And the density of the water is about 957 kilograms per cubic meter. Okay, there are 2 phases, gas phase and liquid phase. Okay, so let's think of another circumstance, the round 3. Round 3, let's increase the temperature here from 100 to 200. Okay, 100 to 200, and then again, it's all the vapors. Here are all the vapors. There's no liquid water, and we start to push this piston down again, and have a guess. The first drop come out, the pressure will more than 1 or lower than 1 here. If you have a high temperature, have a guess. More than 1 or lower than 1. Your PDF file tell you everything, right? So you'll be more than 1. Because what? Because the temperature represents what? Kinetic energy. If you have a very energetic water molecules in the air, in a space, it's very difficult for them to condense. Because if you want to condense the water, that means that you have to make the water molecule get together in a high density. So in that case, you need to have a high pressure. So the pressure will be high, will be more than 1. In this case, it's 15.8. So the first drop come out, the temperature pressure has to reach 15.8 atm. And at this moment, the vapor density, of course, this pressure is high, right? So the density of vapor will be high, which is from 0.5 increased to A density. And the the density of liquid will drop. Okay, will decrease. And again, this is still two phases, gas phase and liquid phase. This is the condition 2. Okay, let's increase the temperature again. Round 4. We increase the temperature to 349.8 Celsius. And then again, you realize in order to get the first drop of the water, you need to increase the pressure. You need to push it down harder. And in this condition, the pressure will be 163. And at this moment, when you measure the density of the vapor increase, the density of vapor increase from A to 113.3. And obviously, this will be decreased, right? The density of the water will decrease. Again, it's two phases. Right. And then what happens if you decrease the temperature? You increase the temperature here, right? And make it as a constant. What happens if you decrease the temperature to 25, which is at room temperature? Okay, so T1 is 25. Okay, and then what's the pressure need in order to get the first drop of the water come out? The pressure will be very, very low, right? Okay, the pressure will be very, very low. And once as you can see, this increase, right? This will be decreased. So the density of vapor will be 0.0234. And the density of the liquid will be 997. Okay, again, these two phases. Right, then let's go to round 5. Increase the temperature again from 349 to 73. As you know, once you increase the temperature, the pressure is getting higher and higher, and even more difficult to make the first drop appear. As you can see, you just increase a little bit, but the pressure increase huge, right? And so the density of vapor will increase. The density of the liquid will decrease. Okay, and round 6. So the round 6 is that if we set the temperature as a 347.15, and then the pressure for the condensation of the water will be 218.3. And at this moment, the density of vapor increase again. And then the density of liquid decrease again. And do you find out something? The interesting thing is that the density of the vapor is equal to the density of the liquid. Why? Because this increase and this is increasing for the density of vapor. This is decreasing for the density of liquid. So eventually they will reach the same level, right? Okay. So the interesting thing is there's still two phases. Okay. So the thing is that what happened to the round 7? If you increase the temperature again, what happened? Will the density of the vapor lower than the density of the liquid? In the case of water, will it happen like this? No, it cannot. So the round 7 is that if the temperature more than 374.15, there's no condensation. There's no water come out. And there's only one phase only. And can we call this phase as a gas phase? No, we cannot. Can we call this phase as a liquid phase? No, we cannot. So how can we call this phase? This is the condition of supercritical. Okay, we call this supercritical fluids. Okay, in Chinese it's 超临界. Okay, so the definition of the TC and PC is that this point is called TC. This point, the critical temperature, is the highest temperature at which a species can coexist in two phases. Okay, is critical temperature of the species TC. So in the case of water, 218.3 is the critical temperature. I'm sorry. The 374.15 is what we call critical temperature. And it's related, the corresponding pressure is called critical pressure. So 218.3 is what we call critical pressure for water. Okay? So just give you an idea, critical temperature and critical pressure. Right, let's go back to this table again. So now you understand water here, as I just make an example for you. The critical temperature is 374.2 Celsius. The critical pressure is 220.5 bar or 220 atm. Okay, so you can find out the critical temperature and critical pressure for all the species. So what is critical, supercritical fluids? So the temperature above the critical temperature and the pressure above the critical pressure, and you will find out this is another phase called critical, supercritical fluids phase. So a substance at the temperature at the TC and the PC is said to be at its critical state. And in this state, we call this fluid supercritical fluids. We use SCF for short. So the substance at the temperature above TC and the pressure above PC are referred as supercritical fluids. So in these figures telling you that the figures on the right hand and left hand side, you can obviously see two phases, right, coexist. And there's a transient state. If you increase the temperature, you can see barely. This is called subcritical, which is it's going to about supercritical, but mada means not yet. Okay, supercritical. And if you increase the temperature again, that will be called supercritical fluids. Right. So just now I give an example of the water. How about carbon dioxide? Carbon dioxide is in solid phase, in the solid state, we call what? 干冰, right? 干冰. So the phase diagram for the carbon dioxide looks like this. The x-axis is temperature, y-axis is pressure, right? Okay, the temperature increase and pressure increase. So you know that the circles represent densities. So as you can see, these circles, you can regard this as a molecular. In the gas phase, the density is very low, right? And then if the carbon dioxide become liquid phase, and then the density increase, okay? But it doesn't pack very well. But if you increase the temperature, if you increase the temperature, if you decrease the temperature and increase the pressure, so the carbon dioxide becomes solid. As you can see that the molecule pack very well. Okay, so the density is high. So the density in solid phase of the carbon dioxide will be larger than the density of the carbon dioxide in liquid phase will be larger than the density of the carbon dioxide in gas phase. Then what happens? If you increase the temperature and increase the pressure above the critical points, then what happens? This phase is called supercritical fluids, right? Supercritical state. Okay? And then, so for this is, the carbon dioxide supercritical fluid is, the temperature will be more than 31.1 Celsius, which is very low. You can just increase the temperature from 25 to 31, you can reach the critical temperature. However, the pressure need to be 72.9 atm, which is very, very heavy, right? Very, very high pressure. Okay, if you reach this condition, the carbon dioxide will be in the supercritical state. Okay, and since this is easier to achieve, this condition is easier to achieve compared to the water, because the H2O, the supercritical state, the temperature is very high, the pressure is also very high. But for the carbon dioxide, it's easier. So here, there are some YouTubers, they make this kind of condition. They make supercritical fluid using carbon dioxide for you to let you have to let you understand what is this. Right. So what's good about supercritical fluids? Just now, the video tell you that there are many applications for you to use supercritical fluids, right? Okay, so what's the property of the supercritical fluid? As you know that in the supercritical for the supercritical fluid, the density of liquid will be very, very high. And so what does that mean? In the case of water, the density of the water, density of the gas, density of the water in the gas phase will be very low. But when you reach to the supercritical fluid, the density of the water of the H2O will be very, very high. And then so supercritical fluids it behaves like liquid in terms of the density. So what's good about high density? If you have a high density, that means the reactivity will be very high, because the concentration of the reactive species will be a lot within a very small spaces, right? So the reactivity will be very high. So, and another property is that, but they also behave like a gas, because the viscosity is, and the diffusion is like gas. The gas, I just told you, the gas, the kinetic of the gas is very high. So the speed of the gas is very fast. That means diffusion will be very fast. So if you have a very high reactive species, and the kinetic energy is also very high, the speed is very high, that means what? The reaction will be very, very fast. Okay, and low viscosity means that the speed of the gas is high. Okay, so you have very good states for the water to be a kind of reactive species. So excellent dissolving abilities. So and also, if you use carbon dioxide as a kind of reactive species, or if you use water as a kind of reactive species, this is kind of environmental friendly chemical, right? Okay, so what can we use this for? The decaffeine of the coffee or tea. You can use these environmental friendly chemicals to decaffeine for the tea or for the coffee. And if you smoke, you can nicotine or tobacco. You can get rid of nicotine from the tobacco. Okay, so you get less harm. And if you have some kind of impurities in your rice and you don't want to eat this rice, the supercritical fluid can help. It can do rice washing. So get rid of the kind of the impurities away from the rice. Okay, from the heavy, you can take away heavy metal. Okay, and dry cleaning too, right? Dry cleaning, and purify contaminating soil, right? So I hope you know that when you go to supermarket, you can see some of the rice. They say that they use some kind of treatment to for you to purify rice, so you can eat more healthy rice. Okay, this is one of the applications for supercritical fluids. Right. So next is that. So I just finished introduction of the supercritical fluids and related to the critical temperature and related to the critical pressure. So now let's define, when you think of the vapor or gas, how do you define vapor or gas? So when you use water, H2O, sometimes you say water vapor, right? Or you call it steam or vapor or gas. So for the supercritical temperature, normally you address the species as a gas when the supercritical temperature when the temperature above the critical temperature. So this is a gas. Gas is a species above its critical temperature at the pressure lower enough. So once you want to address a species as a vapor, that means that the critical temperature, the vapor is a gaseous species below its critical temperature. So in terms of water, the water critical temperature is 374.5 Celsius. So if we have a H2O, which the temperature is about 400, what are you going to address this H2O? Gas or vapor? Gas, right? Because the temperature is more than 374. So here is the question. So the critical temperature and the pressure is of the isopropanol TC is equal to 508.8 Kelvin, and the PC is 53 atm. So propanol is in a gaseous state at temperature is 400 Kelvin and 1 atm. Would it be classified as a vapor or gas? Which one? Will you address the isopropanol as a vapor or gas in this condition? Which one? Gas or vapor? Vapor, right? Because the temperature is less than 508. Okay? Remember this. This might be in your, it might be the Kahoot next week or Wednesday. Right. So now we already introduced you some of the terms that you understand: non-ideal state or non-ideal gases. Okay, and we try to introduce you what kind of equation we want to use for the non-ideal gases. Right. So let's take a look of the first equation I want to introduce you, which is Virial equation of state. So this is ideal gas equation of state, right? P over carat divided by RT equal to 1. What is V over carat? We call specific volume, right? Which is volume divided by mole. So this is what we call V over carat. Okay? So this is ideal gas equation of state. But unfortunately, we want to dealing with the non-ideal gas. So the Virial equation of state tells us that if we add up some terms after 1, then you can just you can modify this equation, ideal equation of state, using these terms. And these terms looks like what? Taylor series, right? Taylor series. So you can have B coefficient, C coefficient, D coefficient, and related with what? With the volume. Okay. So what is B? What is C? What is D? So this is only for single species. Virial equation of state is only for single species. And V over carat is what we call specific molar volume. Specific molar volume. And Virial equation has a theoretical base in statically mechanics. So B is well developed, but not others. So what I want to tell you is that, if you study thermodynamics, you can realize the physical meaning of B. But of course, you are in the first year only. When you go to the third year of the chemical engineering, you can realize, you can study thermodynamics, and you will realize how to find out B. But here is out of scope in our case. So anyway, what I want to tell you is that B is well developed, but not others, but not C or D. Okay? So if B equal to C equal to D equal to 0, then this will become what? Ideal gas equation of state, of course. So Virial equation is like this. And then if we, regardless of C, D, we only think of B, that means we use truncating C, D, and E. And this will be what we call truncated Virial equation. Truncated Virial equation, which is P over K rod divided by RT equal to 1 plus B divided by V over K rod. Okay, only these terms apply, and we use this as a truncated Virial equation. Okay? And the Virial equation used in what? Non-polar species. Is this kind of gas is easier to dealing with, but not for polar compounds like H2O is difficult. Right, Virial equation. So how to get B? No, important thing is how do we get B here? And you don't need to remember this, but what I want to tell you is that B is equal to this. Parenthesis RT divided by RTC divided by PC times blanket B0 plus omega B1. So what is, so B is this, right? So R is gas constant. TC is what? Critical temperature, right? You need to know the TC of the air or the nitrogen, or TC of the oxygen, for example. This PC is critical pressure, right? How about B0? Another coefficient. How about omega? Omega is called pizza eccentric factor. I will show you later. B1 is another coefficient. So B0 is this. B0 is 0.083 minus blanket 0.442 divided by TR power 1.6. What is TR? TR is what we call reduced temperature. Reduced temperature. And we know the B1. So ladies and gentlemen, I don't want you to remember these numbers. If this show up in your final exam, I will give you this equation. But obviously, this is too easy. I don't think I will give you this as an exam in your exam paper. Anyway, but you need to remember what is TR. We call reduced temperature. And the B1 here is 0.139 divided by blanket 0.172 divided by TR power 4.2. So what is TR? TR is what we call reduced temperature. The definition of TR is this. Ladies and gentlemen, please remember this. TR equal to the temperature divided by critical temperature. Okay? So, and what is omega? For the non-polar species, normally we use pizza eccentric factor. You might say, well, Professor, you just tell me that Virial equation of state is applied to the non-polar species. But now you say that it's non-polar species, you still need to use pizza eccentric factor. What's that? Well, this is a factor. Just remember this. Okay, I'll show you in the next page. So parameters that reflect the geometry and polarity of the molecule. So in your textbook, table 5.3-1 on page 201. But anyway, I'm showing you here. So this is what we call pizza eccentric factors. Pizza eccentric factors is that how far this is from ideal gas. The number is showing you how far this is from ideal gas. So the parameters that reflect it to the geometry and polarity of a molecule. So that means that this, if the number is high, that means it's a polar molecule. If the number is low, almost zero, close to zero, that means it's a polar molecule. For example, here is that what I want to show you, argon. Eccentric factor is almost zero. right? And methane is CH4, right? CH4. So you have one carbon in the center and another 4 hydrogen will distribute evenly in the space. So this is a non-polar molecule. So methane is the eccentric factor is 0.008. And oxygen is 0.21. So as you can see, that they are very low because they are almost non-polar molecular. But when you take a look of the water, the pizza eccentric factor is high. Why? Because this water is a non-polar molecular. Okay. Right. So this is an example for you to use truncated Virial equation of state. Example 5.3-1. Let me see that. 5.3-1. Okay. So let me see that. Okay, I will read this for you. Is that 2 grams moles of the nitrogen is placed into a 3-liter tank at the minus 150.8 Celsius. So 2 gram moles of the nitrogen, you got a mole, right? And then 3-liter tank, so you got a volume. And the temperature is minus 150.8, you got temperature. So now you want to evaluate the pressure, okay? So you can use ideal gas equation of state to evaluate the pressure. You can also use the truncated Virial equation state to measure to calculate the pressure, right? Okay, so for the idea, so if you use ideal equation of state, the pressure will be 6.73 atm. And then how about truncated Virial equation of state? So you have this. I just show you here everything. Okay. And the answer you will get is 6.19. So this what does this tell you? What does this telling you? If you use ideal equation of state, and the P ideal will be 6.73. But if you use truncated Virial equation of state, the pressure will be 6.19. So the epsilon will be what? Will be P ideal divided by P, right? And divided by P. Minus P and divided by P, which error is about 8.7. So as you can see, in this case, it's not a good idea to use ideal equation of state to measure to calculate the pressure. Instead, you need to use truncated Virial equation. Okay, why? Because temperature is too low, minus 150. You know, when we want to use the ideal equation of state, the temperature generally need to more than 0 Celsius. The pressure need to lower than 1 atm, right? That's what we learned today in the Kahoot, right? Right. So that was the first equation, and second one here is called BWR equation. Okay, there are 8 empirical constants. Okay, for the light hydrocarbon and nonpolar gases. You can find out this in empirical chemical engineering handbooks. And I will skip this. For the summary of the Virial equation of state, here is that Virial equation of state is this one. And you have truncated Virial equation of state, right? So you need to find out B. And in order to find out B, you need to find out B0 and B1 and omega. And then in order to find out B0, you need to find out TR. And here you need to remember TR is reduced temperature, which is temperature divided by critical temperature, right? Okay. And then B0, B1, in order to find out B1, you need to find out TR again. Right. And omega and TR is this reduced temperature. And finally is omega, right? Omega. you can check it in the table. So check in the table, you need to find out 3 omega Tc and Pc for the pressure for the species you want. Right. Next topic will be 5.3c cubic equation of state.